Welcome everyone. Today we're diving deep into Azure site-to-site VPN implementation. This is one of the most crucial technologies for connecting your on-premises infrastructure securely to Azure. Throughout this presentation, I'll walk you through every aspect, from basic concepts to advanced configurations. We'll cover the architecture, design considerations, and step-by-step implementation using Azure CLI commands. By the end of this session, you'll have a complete understanding of how to design, implement, and troubleshoot Azure site-to-site VPN connections in production environments. Understanding the architecture. Let me start by explaining the fundamental architecture of a site-to-site VPN. This diagram shows how we create a secure tunnel between your on-premises network and Azure. On the left, we have your on-premises network with the IP range 10.0.0.0/16. This connects through your on-premises VPN gateway, which has a public IP address that Azure can reach. In Azure, we create a virtual network with a different IP range 10.1.0.0/16 to avoid conflicts. The key component here is the virtual network gateway, which sits in a special subnet called the gateway subnet. The magic happens when these two gateways establish an encrypted IPsec tunnel over the internet, allowing secure communication between both networks. Design considerations. Now let's talk about the critical design decisions you need to make. First is the gateway SKU selection. This determines your performance, features, and cost. The basic SKU is only for development environments. For production, you want VPN GW1 or higher, which gives you BGP support and active capabilities. VPN GW2 is my sweet spot for most production workloads. It gives you 1 gigabit per second throughput and supports up to 30 tunnels. For enterprise scenarios with high bandwidth requirements, VPN GW4 and VPN GW5 can handle up to 10 gigabits per second. Remember, you can always scale up your SKU later, but scaling down requires recreating the gateway, which means downtime. High availability design. This is where things get really interesting. For production workloads, you never want a single point of failure. The diagram shows an active configuration with full redundancy. On the Azure side, we deployed 2 gateway instances with 2 public IP addresses. On premises, you have 2 VPN devices. This creates 4 IPsec tunnels total, providing maximum availability. If any single component fails, 1 Azure gateway instance, 1 on-premises device, or even 1 tunnel, traffic continues flowing through the remaining paths. This is enterprise-grade availability. The beauty is that Azure handles the load balancing automatically, and you get increased throughput since traffic can use multiple tunnels simultaneously. Policy versus route-based VPNs. This is a crucial concept that often confuses people. Let's break down the difference between policy-based and route-based VPNs. Policy-based VPNs use traffic selectors. They look at the source and destination of each packet and decide whether to encrypt it based on predefined policies. It's like having a bouncer at a club with a specific guest list. Route-based VPNs work differently. They use routing decisions. If a packet needs to go to the remote network, it gets sent through the VPN interface. It's more like having highway signs that direct traffic. Route-based is the modern approach and what I recommend for Azure. It supports BGP, multiple tunnels, and is required for Azure-to-Azure connections. Implementation Step 1. Foundation. Now let's get our hands dirty with the actual implementation. We always start with the foundation, creating our resource group and virtual network. The resource group is your logical container. I use a naming convention that includes the purpose, environment, and location. This makes management much easier as your Azure estate grows. For the virtual network, notice I'm using 10.1.0.0/16. This gives us 65,536 IP addresses. Make sure this doesn't overlap with your on-premises networks. I've seen this mistake cause hours of troubleshooting. The location should match where your users are. And remember that VPN gateways can't be moved between regions once created. Implementation Step 2. Subnet configuration. Subnet design is critical for VPN gateways. You need two types of subnets. One for your actual resources, and the special gateway subnet. The VM subnet is straightforward. Size it based on how many resources you'll deploy. A 24 subnet gives you 254 usable addresses, which is plenty for most scenarios. The gateway subnet is special. The name must be exactly gateway subnet, case sensitive, and I recommend a 27 minimum. This gives you 32 addresses, allowing for future gateway scaling and high availability configurations. Pro tip: even if you're starting with a single gateway, always size the gateway subnet for active. You'll thank me later when you need to upgrade. Implementation Step 3. Public IP and Gateway. Here's where we create the actual VPN gateway. The public IP configuration is crucial. Always use standard SKU and static allocation for production. I'm specifying availability zones here, which distributes the IP across multiple data centers for additional resilience. This is included with standard SKU at no extra cost. The gateway creation is the longest step, typically 20 to 45 minutes. That's why I use the no wait flag, so I can continue with other configurations while it deploys in the background. Notice I'm using VPN GW2 SKU with Generation 2. The newer generation supports better encryption algorithms and improved performance. Always use Generation 2 for new deployments. Implementation Step 4. Local Network Gateway. The local network gateway is Azure's representation of your on-premises network. Think of it as Azure's address book for your local site. The gateway IP address must be the public IP of your on-premises VPN device. It needs to be static and reachable from the internet. No NAT or firewall blocking, please. The address prefixes are crucial. These tell Azure which traffic should be routed through the VPN tunnel. You can specify multiple prefixes if you have complex on-premises networking. If you're using BGP, you'd specify the BGP peering address and ASN instead of static address prefixes. BGP is fantastic for dynamic environments where networks change frequently. Implementation Step 5. VPN Connection. Now we create the actual connection between Azure and on-premises. This is where the magic happens. The shared key is critical. It must match exactly on both sides. I recommend generating a strong, random key of at least 64 characters. Store this securely in your password manager or key vault. The routing weight helps with path selection when you have multiple connections. Lower numbers have higher priority, but this only matters if you have redundant paths. Once this command completes, you still need to configure your on-premises device with the corresponding settings. The tunnel won't come up until both sides are properly configured. Now, let's look at the IPsec/IKE negotiation process. Let me explain what happens when the VPN tunnel is established. This sequence diagram shows the two-phase IPsec negotiation process. Phase 1 is IKE main mode. Both gateways exchange encryption proposals and authenticate using the shared key. This creates the IKE Security Association. Phase 2 is IPsec quick mode. They negotiate the actual data encryption parameters and create the IPsec Security Association. This is what protects your data. Once established, all traffic flows through the encrypted ESP tunnel. The custom IPsec IKE policies. Sometimes Azure's default IPsec policies don't match your on-premises device requirements. That's where custom policies come in handy. The parameters shown here represent strong, modern encryption. AES-256 for encryption, SHA-256 for integrity, and DH Group 14 for key exchange. These are good security standards for 2024. The SA lifetime determines how often keys are refreshed. 3,600 seconds, 1 hour, provides good security without excessive renegotiation overhead. Always match these parameters exactly on both sides. A mismatch in any parameter will prevent the tunnel from establishing. I keep a checklist to verify all parameters match during troubleshooting. When VPN connections don't work, I follow this systematic troubleshooting approach. It saves hours of random configuration changes. Start with the basics. Is the gateway deployed and running? Then check if the connection object shows connected status. These are quick wins that eliminate common issues. If the connection shows as disconnected, verify the shared key matches exactly. Case sensitivity matters. Then check if IPsec policies are compatible between both sides. For traffic flow issues, examine route tables and network security group rules. Often the tunnel is up, but traffic is blocked by security rules or routed incorrectly. The key is methodical testing. Change one thing at a time and test the result. These diagnostic commands in the Azure CLI are your best friends for troubleshooting VPN issues. Let's walk through each one. First, the command to check basic gateway status. If this shows anything other than succeeded, you have a gateway deployment issue, not a VPN configuration problem. Next, the connection status command. This shows whether the tunnel is established and includes data transfer statistics. 0 bytes transferred usually indicates a routing or security group issue. The troubleshooting command is very powerful. It runs comprehensive diagnostics and generates detailed logs. The results are sent to a storage account for analysis. For BGP-enabled connections, the BGP commands show peering status and learned routes, which is invaluable for dynamic routing scenarios. Azure Extended Network. This fascinating technology bridges Layer 2 networks between on-premises and Azure. Let me explain how this works. Traditional VPNs operate at Layer 3. They route IP packets between networks. Extended Network operates at Layer 2, extending your actual on-premises subnet into Azure. This means Azure VMs can get IP addresses from your on-premises DHCP server and exist on the same broadcast domain as your physical servers. It's like the Azure VMs are physically sitting in your data center. This is incredibly useful for migration scenarios where applications have hard-coded IP dependencies, or for disaster recovery where you need identical network configurations. However, it requires Windows Server 2019 Plus with Hyper-V and has geographic limitations. Not every scenario needs this complexity. Command execution flow. This flowchart shows the optimal order for executing our deployment commands. Following this sequence prevents dependency errors and reduces deployment time. The critical path is the virtual network gateway creation. It takes 20 to 45 minutes and everything else depends on it. That's why I started early with the no wait flag. While the gateway deploys, you can create the local network gateway and any other supporting resources. Just monitor the gateway status before creating connections. The decision diamond for BGP highlights that BGP configuration is optional but powerful. If your on-premises equipment supports it, BGP provides automatic failover and route learning. Following this flow, total deployment time is dominated by the gateway creation, not the sum of all commands. Deployment timeline and optimization. Let me share some real-world timing and optimization strategies I've learned from deploying hundreds of VPN gateways. The resource group and v.net creation are fast, under 2 minutes total. Subnets are nearly instantaneous once the v.net exists. Public IP creation is quick, but don't forget to use standard SKU for production. The extra features are worth the minimal cost difference. The virtual network gateway is your bottleneck. Plan for 30 to 45 minutes. Higher SKUs sometimes take longer due to additional provisioning requirements. Pro tip: use multiple terminal sessions. Start the gateway creation in one session with no wait, then create other resources in parallel. This can cut your total deployment time in half. Best practices and security. Let me share the most important best practices I've learned from production deployments and security incidents. Always use strong shared keys, 64+ characters with mixed case, numbers, and symbols. I've seen environments compromised because someone used password 123 as their VPN key. Implement network security groups to control traffic flow. Just because the VPN tunnel is established doesn't mean all traffic should flow freely. Use route-based VPNs with BGP when possible. The dynamic routing capabilities will save you during network changes and provide automatic failover. Monitor your connections actively. Set up Azure Monitor alerts for tunnel status changes and unusual traffic patterns. Document your IPsec parameters. You'll need them for troubleshooting and when you add more sites. Common pitfalls to avoid. Let me share the most common mistakes I see that cause hours of frustration and unnecessary downtime. The gateway subnet name must be exactly gateway subnet, using that specific casing. I've seen teams spend days troubleshooting because they used gateway subnet or gateway subnet. IP address overlap is another killer. Your Azure v.net and on-premises networks must use completely different IP ranges. Plan this carefully before deployment. Don't forget firewall rules on your on-premises side. The IPsec traffic needs to flow through UDP ports 500 and 4500. Test with simple resources first. Deploy a basic VM and test connectivity before moving production workloads. This isolates VPN issues from application problems. Always have a rollback plan. Know how to quickly disable the connection if something goes wrong. Summary and next steps. Congratulations! We've covered everything you need to implement Azure site-to-site VPN connections successfully. We started with architectural concepts, discussed design considerations like SKU selection and high availability, and then walked through the complete implementation using Azure CLI commands. We covered troubleshooting methodologies, advanced features such as Azure Extended Network, and shared real-world best practices and pitfalls to avoid. So, what are your next steps? Start with a test environment, practice these commands, and gradually move to production. Remember that every environment is unique, so adapt these patterns to your specific requirements. Don't hesitate to start small and scale up. You can always upgrade your gateway SKU and add high availability features as your needs grow. Thank you for your attention, and good luck with your Azure VPN implementations.